So we did nomenclature for benzene rings, right? Letters for dye substituted, numbers for everything else. There's two more nomenclature things we need to go over to kind of finish that off. And the first is when we have benzene as a substituent. Right, so a situation where a benzene ring is on a chain that has more carbons than the benzene ring itself, right? So our parent hydrocarbon here is this, and we have the benzene ring hanging off of it. All right. So when benzene is a substituent, we call it phenyl. You're going to be angry here in about 5 minutes when I tell you that there's also a thing called a benzyl group that is not this. For right now, it's phenyl. So when you have benzene as a substituent, this would be like 3 phenyl, 4, 5, 6, 8, like 3 phenyl octane. Now, as I have established, I think through 2 semesters, is it organic chemists are lazy, and if we can avoid drawing stuff, we will. And so phenyl gets abbreviated pH. So if you see a pH on a molecule, that is just a benzene ring hanging off the molecule, right? So the pH equals just a benzene ring. So this would be phenyl cycloheptane. Seem reasonable? Like I said, deep down, you feel like that every time anything else has been a substituent, you took its name and you threw YL on it. So you feel like benzene should have become benzol. But don't worry, we used benzol for something else. Yeah, right? So there's something called a benzyl group. The benzyl group is a benzene ring with a CH2 and then attached to something else. So a benzyl is a benzene ring plus a CH2. Rules comfortably beneath. Just don't give me that look. Right? So this whole thing, this is a benzyl group. And it's abbreviated BN. It's very good, BN. So the reason that it's called a benzyl group is, so do you remember on double bonds we had the vinyl carbon and then the allylic carbon, the carbon beside the double bond? On an aromatic ring, the carbon bonded to the aromatic ring is the benzyl carbon, is benzylic. So a benzyl group is when you have something attached to the benzyl carbon. We call it a benzyl group. So a lot of times you'll see benzyl groups hanging off of, like, this uses a protecting group, so it'll be hung off of like a nitrogen or an oxygen. But you can have stuff like this. See here, like we had like a long chain, right? You could say, hey, this is my longest chain, and I have a CH2 benzene ring hanging off of it, so that would be a benzyl. So this is 4 benzyl octane. Or a lot of times it might be That's only because of this. You go from phenyl to benzyl because now you're naming this entire thing that is the aromatic ring plus that benzyl carbon plus that CH2. Right, so here this would be 1, 2, 3, 4, 5, 6, 7, 8, 8 again. So this would be octane for amine. And on the nitrogen, you have a CH2 and a benzene ring. So this would be N-benzyl octane for amine. And again, just like the pH, we can use Bn to substitute us having to draw the ring. So you could have kind of what we did before. Right? The Bn is taking the spot of the CH2 and the aromatic ring. So if you just see Bn, it's CH2, then a benzene.
The question was, is it still a benzyl group if there are like two carbons between the aromatic ring and the chain or the nitrogen, or if there's a group coming off of the benzylic carbon?
Then it's not a benzyl group. So if there's two carbons, it's different. It has to only be one. It has to be a CH2 and then a benzene. If there's two carbons, it has a different name. If it's a CH that has a different group coming off of it, it's a different name. So just CH2 benzene ring, that's benzyl. So I always try to prove to you that these compounds, these things that we talk about, have like real world applications. So I give you drugs. So we have the first thing, dopamine, right? Makes you happy and whatnot. If you look under dopamine, you have MDMA, that's ecstasy, right? So a lot of neurotransmitters have the same base structure of they have an aromatic ring, they have two carbons and then a nitrogen. You dress them up different ways, but you get um, but they all kind of have that same base structure. They're all kind of binding to very similar places, so they have similar structures. So, Adderall, right? You have that same structure with an NH2 on it, nothing on the aromatic ring, right? I don't know, makes you do your homework, focus up real hard. I went to when I was a postdoc, one of the grad students was like, yeah, man, I'm going to go home and take some Adderall and then clean my house. But if I touch a Wii controller, that's all I'm going to do for 7 hours. He was like, I've just got to, he's like, I just have to focus on cleaning my house. But if I do anything else, I'm going to lock in on that. I was like, you could just clean your house without filling up first. Like, that could be an option. Now, Adderall, your doctor will give you that if you need it. If you put a methyl group on that nitrogen, you get methamphetamine. If your doctor gives you that, they're a very bad doctor. You let them behind, like, in an alley behind a liquor store. That's a bad doctor, right? So the difference between Adderall and methamphetamine, is like studying and like hating your teeth, is one methyl group, right? So if you put a methyl group on Adderall, you get methamphetamine. It's bad. So we have up top OxyContin. This number for OxyContin, like the numbers of sold, these are pretty old at this point. But at one point, OxyContin had made, I think this is like from 2014, made like $3.55 billion in sales for the year, right? If you look at it, right, you've got the aromatic ring. This is right. Sorry, Zoom, I got a point over here. Then you've got carbon, carbon, nitrogen, right? The same structure as you have for dopamine. Aromatic ring, carbon, carbon, nitrogen, right? So you have that same structure repeating again. And then you change a little bit of functionality around it, and you get heroin, right? The difference between heroin and morphine, it's so where the oxygen that comes off the aromatic ring and the oxygen that has chirality down by the double bond, if you take that acetate group off, the C double bond O, CH3, if you take both of those off, you get morphine. Your doctor might give you morphine. Again, your doctor's bad if they give you heroin. Or your doctor's from like 1900 and it's a cure-all. Simple times, man. So a lot of your opioid pain relievers are built on this structure, and you've just changed like you've turned one hydrogen into an oxygen. So like fentanyl is like this structure, but I think there's like an oxygen here, which makes it like 10,000 times more potent. Like you change I think you change the wedge hydrogen by the nitrogen into an oxygen or something, and it becomes way more potent. So it's just small changes get you different effects. Then down at the bottom left, you have 2CI, which is called smiles. So drug dealers are way more inventive than we give them credit for. So there's a guy whose entire research program, he's at a university, is he makes psychoactive compounds. And then he publishes papers where he's like, hey, I made these compounds, right? You have to if you publish your paper. That's what they do. They go through his papers and they make the compounds that he talks about. Then they take them and they try to see like which ones give a good high or not, or which ones are easy to make that they can sell. And that gave us 2CI smiles. And apparently, this story I read when I found this molecule, now this has been like 10 years ago or 8 years ago, people would take it and then film themselves and like post it to YouTube. Basically, the plot line of like 21 Jump Street, right? And they described it as quote unquote a roller coaster ride through hell, which sounds like the worst way to spend a Friday night. Like that sounds awful. Like what are you gonna do, dude? I'm gonna go give $50 to a stranger. He's gonna give me some white powder, and then it's gonna be like a roller coaster ride through hell that I'll record and post on YouTube. That sounds awful. Sounds awful. Yeah, no, don't do that. And then bottom right is tryptophan. That's the part of turkey that makes you sleepy, right? So all of these compounds are all kind of unified by having that aromatic ring in them. A lot of pharmaceuticals, I got to pick a million other things. A lot of pharmaceuticals are built on the back of putting aromatic rings together because that's something we're really good at as people, as chemists, is putting aromatic rings together. So we're able to kind of use aromatic rings as like building blocks and snap them together and get functional groups to hang off of them so that we can get functional groups in the right place to go bind to an enzyme or a receptor and get an effect. So we're really good at like snapping them together. So a lot of pharmaceuticals are kind of like three zones, and they're usually just aromatic rings stuck together to make each of the zones, with benzene being like the simplest one. So there you go. Look at that. Nice informative thing. Yeah. Yeah. What is it? Oh, Oxycontin. Part of the reason up here is this is a deep TV cut. You guys probably don't know it, but that's fine. Oxycontin is called hillbilly heroin. All right. And way back when, you guys were probably like in elementary school, right? There was this show called Buck Wild on MTV, and it was about like rednecks in West Virginia, like playing with construction equipment and like making swimming pools out of the back of pickup trucks, right? It lasted like a season or two. But one of the girls on the show, after the show got canceled, she got arrested with a trunk full of Oxycontin. So she got arrested for intent to distribute. And I was like, thanks, West Virginia person. Like people know like seven of us, and one of us is now in jail for trying to like push hillbilly heroin. Thank you very much. Could you have done anything better? I don't know. Could you have like done securities fraud? Oh wow, that's a smart person crime. No. We did like, ooh, let's sell some drugs out of the back of a Pinto. It's like, no, no. All right. So we're going to talk about the structure of benzene and some of why the structure of benzene leads to its stability, or how it explains why benzene is stable. So let's see the structure. All right. So benzene has some unique structural features, some things that are you would not expect. The first is if you look at benzene, all the bond lengths are exactly the same. So, right, when you draw it, you got your double bond and your single bond. All the bond lengths are 1.39 angstroms. All right, and that is in between a double bond and a single bond. A single bond is 1.54 angstroms. A double bond is 1.34 angstroms. So we are in between a single bond and a double bond based on length, right? When you're in an in-between spot in bond length, we say that you kind of have like a half bond order. So all the bonds are 1.5 bond order, which means they're not quite a double bond because they're not quite short enough, but they're also not quite a single bond because they're not long enough. So we say it's in the middle. It's like 1.5 bond order. Right, so there's not like benzene has distinct double bonds and single bonds. We touched on this last class, right? It's all the bonds are the same and they're all almost a double bond or like halfway between a double bond and a single bond. All the carbons in benzene are sp2 hybridized. Right, so every carbon is sp2 hybridized, so they all have a double bond, right? This means that benzene is flat. So the benzene ring sits perfectly flat on the page of your page, in the plane of your paper or screen or whatever you're looking at this on. Your phone, whatever. Right? It is 100% flat in the plane. Because every carbon is sp2 hybridized, all the bond angles are the same. Right? These bond angles, let's pick a different color here. Bond angle is 120 degrees. So all the bond angles are the same. They're all 120 degrees. And because we have this double bond, single bond, double bond, single bond, double bond motif around it, the double bonds don't act like you would expect them to, right? It's not like we have a cyclohexane with 3 double bonds in it. If you figured out how much energy or how stable that molecule would be, benzene is way more stable than you would expect it to be. So if you were to just add up like the energy of a cyclohexane and then add the energy from 3 double bonds to it, this and benzene isn't being more stable than you would predict because of how the double bonds interact with each other. Right. So it's gonna be artistic now. Right. So all the double bonds in benzene are conjugated. right? Again, have resonance. Right, so like we drew on Monday, right, you're able to have your double bonds move around the ring. Right. So the way this kind of looks is I'm going to draw the benzene ring kind of on its side. Right, your orbitals stick up out of the benzene ring. Right, so each carbon has a p orbital that is perpendicular to the plane of the benzene. So like I've kind of taken the benzene, it's a little fugly, but I've kind of turned it on its side. So you're looking at like the edge of the benzene, and above and below the plane that the benzene makes, you have your p orbitals on each carbon. Since they're all sp2 hybridized, they all have a p orbital, right? And you get your overlap, which makes your double bonds, right? And you got your two different versions, your two different resonance structures, right, where the double bonds have moved a little bit. Now, if that happens fast enough, right, for you to make a double bond, your p orbitals have to overlap, right? They have to kind of smush together and make that bond, right? If that happens fast enough, what ends up happening is you lose those unique double bonds, and those orbitals all end up being smushed together to make one big orbital. So I'm going to go to the next slide. What you end up with is like a donut of orbitals above and below the plane of the benzene ring. Right, so you end up with this donut of electrons above and below. So think of it like a hamburger with like donut buns, which is like a thing that happens for some reason, right? You've got donut, burger, donut. Here you've got electron donut, carbon burger, electron donut, right? So you lose the distinct double bonds because they're moving, those electrons are moving around so fast, you just make one big orbital so they can move quickly around. So the reason benzene's more stable than you would think is those orbitals stop being unique and they just become one big orbital that is cohesive and working together. And to do anything to one double bond causes you to mess with all the double bonds. So that's what makes benzene so stable, is it's hard to kind of break up these big orbitals that have all the electrons in them working together. Right? Because you have all these resonance structures, right? You can also just go back to the simplest thing about stability, right? More resonance structures equals more stable, right? So since I can have these resonance structures and I have all these electrons working together, it's just more stable because I have resonance structures. So kind of the hallmark of being aromatic is you're a ring and you have all your p orbitals are kind of together and making one of these big orbitals above and below the plane of the ring that you are, right? And that leads to more stability. So because science is weird, this kind of idea of the one big orbital came from a dude taking a nap. So Huckel was thinking about benzene, and he was on a train, and the story goes he fell asleep, and he had a dream about a snake eating its own tail, and how that would cause the snake to just be a circle, or, the Ouroboros, right? It would just cause it to be a circle. And he woke up and he's like, that's what benzene does. The electrons kind of chase each other, right? and they just cause themselves to be one big circular orbital as opposed to unique orbitals. I don't know what he ate before that nap. It must have been something that was a little trippy. Yeah, he had some smiles beforehand. It was like, oh, dude, this is like a train ride through hell. And then, like, had this dream about a snake eating itself. I'm just opening up my perspectives, man. It's like, calm down, dude. All right. Make sense? Seem good? The benzene is not the only aromatic compound. I want you to be able to look at a compound and determine if it is aromatic or not. So I'm going to give you a checklist. And if you work down my checklist, you will always know if a compound is aromatic or not. Right? So let's talk about how we identify. Right. So there are three things that an aromatic compound needs to be. All right. So to be aromatic, you need to be a flat ring. Now, the flat ring thing, that is good. The flat ring thing is the hardest thing for me to expect you to know how to do, because there are some things that I can draw that look flat but aren't actually flat, right? So what I do is the flat ring is just a throwaway, in that if I draw something, I want you to assume it's a flat ring. All right? So basically, everything I draw, if I'm asking you, hey, is this compound aromatic or not? You're just going to assume the thing that I drew is a flat ring. I'll show you the like quintessential example of like why I do this in a bit. But you're just going to assume, hey, this is a flat ring. Right? So the second thing is each atom must have a p orbital. I should specify each atom in the ring must have a p orbital. Right? So just like on benzene, every carbon had a p orbital. For any aromatic compound, each carbon or each atom that makes up the ring has to have a p orbital, because to be aromatic, your electrons have to be able to freely move all the way around your ring, right? So if one carbon's missing a p orbital, the electrons go and then they hit that carbon that doesn't have a p orbital, or that atom that doesn't have a p orbital, and they have to stop, right? So every atom has to have a p orbital all the way around, right? And then the last one is the ring must have a 4n plus 2 number of electrons. So if you count all the electrons that are able to move in this uninterrupted pi chain that you have going around your ring, they must add up to a 4n plus 2 number. Now, this is where I have to stress there's nothing about the ring or its structure that tells you what n is. 4n plus 2 just lets you have, it's just basically a counting game, right? Because I could make you memorize a bunch of numbers. I could say, to be aromatic, you have to have 2, 6, 10, 14, 18, 22, 26, 30 electrons, so on and so forth. Or I could be like, you have to have a 4n plus 2 number of electrons. If n is 0, this ends up being 2 electrons, right? If n is 1, it's 6. If n is 2, it's 10. So instead of having to memorize each individual number, right, you can just count up your number of electrons and go like, oh, I have 20 electrons. Is 20 a 4n plus 2 number of electrons? And you're like, no, right? Because if n is 4, I get 18. If n is 5, I get 22. 20 is neither of those numbers. Thank you, Sesame Street. This is not an aromatic number of electrons, right? So the 4n plus 2 just lets you like know what numbers you have to like you have to have in your aromatic ring without having to memorize, without having to go like 102. That's 4n plus 2 because I memorized all the other ones. But like 102, if I throw 25 in for n, I get 102. Cool, right? So don't like look at a ring and go like, oh, this compound only has one ring, so the n must be 1. It's like, no, it has nothing to do with the structure. It's just letting you like play a counting game as opposed to have to memorize everything.
The question was, so we could determine 4n plus 2 without seeing the structure?
I could tell you that I could say I have a compound that is a flat ring. Every atom has a p orbital, and it has 38 electrons. Is it aromatic? And all you have to do is figure out, is 38 a 4n plus 2 number of electrons? It is. So it doesn't matter what the structure is. If I tell you flat ring, everything has a p orbital, and give you a number of electrons, you can figure out if that number of electrons is 4n plus 2. Yes, ma'am? It doesn't represent the number of p orbitals. It represents the number of pi electrons. I will show you. We're going to do a bunch of examples. It'll make a ton of sense. All right. So what I do, so we'll start with benzene. You know the answer to benzene. You know it's aromatic, right? So if you have benzene, what I like to do is I like to say, okay, flat ring, check. Right? That is our default, is a flat ring. Right? Now, p orbitals. Does every atom in the ring have a p orbital? We know that, so basically what we're looking for is, in the simplest cases, is every atom part of a double bond? Right? So even though this double bond is really short for some reason, there you go, right? This carbon's part of a double bond, this carbon's part of a double bond, this one is, this one is, this one is, and this one is. Be part of a double bond means you have a p orbital. So every atom in my benzene ring has a p orbital. So I have met the p orbital requirement. Now I need to figure out how many electrons I have. So to figure out how many electrons you have in your pi system, in that like uninterrupted chain of p orbitals, you count your double bonds. Every double bond is worth 2 electrons. So I've got 2 electrons, 2 electrons, 2 electrons. So I have 2, 4, 6 electrons total, right? Six electrons. Is 6 a 4n plus 2 number of electrons? Well, if n is 1, 4 plus 2 is 6. It is 6 is a 4n number of electrons. So benzene is aromatic. Again, when we're doing these, we're just going to assume that I've given you a flat ring. Does every atom in this top structure have a p orbital? Is every atom part of a double bond? Right, so every atom is part of a double bond. So here, 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 here. If I just keep saying here, it'll get super annoying, so I'll just stop. Right, so everything's part of a double bond, so everything has a p orbital, so we've met that rule. How many electrons do I have? I have 10 electrons. Is 10 a 4n plus 2 number of electrons? It is. So this compound is aromatic. This is naphthalene. This is the part of mothballs that smells bad. As the smell of mothballs is naphthalene. Is everything part of a double bond? Does every atom have a p orbital? Yep. So we're good. How many electrons do I have? 14. Is 14 a 4n plus 2 number of electrons? Yep. So this is aromatic. In all honesty, right, while 4n plus 2 could let me say like, oh, I know, 282, is that a 4n plus 2 number of electrons? Realistically, like, maybe we get to 14 or 18 electrons like on an exam. Like, it's really hard to start drawing some really big, dumb structures that get many more electrons than that. So, like, if you have it pretty well nailed down, like 14 and 18, you're good. Right? So, if we look at a ring and you say, hey, is it a flat ring? Does everything have a p orbital? How many electrons are there? It's aromatic. So, if like cartoons have taught me nothing in my life, where there is good, there must be evil. Where there is stability, there must be instability. Yes, where there is order, there must be chaos, right? So, we have aromatic compounds that are very stable. Then we have the kind of the opposite of aromatic compounds, which are called anti-aromatic compounds. Right? So anti-aromatic compounds right? So anti-aromatic compounds are flat rings that have a p orbital on every atom, but they don't have a 4n plus 2 number of electrons. They instead have a 4n number of electrons. So they otherwise look like they're going to be aromatic, but they have the wrong number of electrons. So if you have this, you're like, okay, Wakefield told me it's a flat ring. He wouldn't lie to me for the most part, right? Everything has a p orbital. Everything's part of a double bond. All right. And I only have a 4n number of electrons. They only have 4 electrons. This compound is anti-aromatic. Now, anti-aromatic compounds, for the most part, like 99% of them, we can't make them. They're so unstable that if you try to make them, they won't form. Basically, compounds will do anything they can to avoid being anti-aromatic. Either the reaction that you're doing to try to make them just won't happen, or the molecule will change in some way so it's not anti-aromatic. So if you're flat, have a p orbital, 4n plus 2, you're aromatic. If you're flat, have p orbitals on every atom, and have a 4n number of electrons, you're anti-aromatic. If you break either of the first two rules, either you're not a flat ring, or you don't have a p orbital on every atom, you are non-aromatic. So non-aromatic compounds. All right. So we've got aromatic compounds, flat ring, p orbital on every atom, 4n plus 2 number of electrons. Anti-aromatic compounds, flat ring, p orbital on every atom, 4n number of electrons. And then if you break one of the first two rules, if it's either not a flat ring or there's not a p orbital on each atom, that compound is going to be non-aromatic. So a lot of times a compound that could be anti-aromatic will twist itself or fold so that it's not a flat ring anymore. So it breaks the first rule. So it doesn't have to be anti-aromatic. So this is why I tell you guys to just assume everything I draw is a flat ring. And here's why. Here's like the kind of the quintessential example. So we can buy cyclooctatetraene. I draw it and you're like, oh, it's a flat ring. I feel good. But what it does is it never lays flat. Cyclooctatetraene instead folds itself into like a big boat, a yacht, if you will. All right. It folds itself into a big boat, so it never sits flat. So it breaks the first rule of being aromatic or anti-aromatic. It's not a flat ring. So it can be formed because it's able to fold itself and not be flat. So I can't expect you to look at a compound and go like, oh, this one can totally fold itself. So it's going to break the first rule. That's why I tell you just assume everything I give you is a flat ring, because it's not fair for me to be like, well, this is a big ring. Clearly, you should have known it was going to be have a different shape. That's not cool, right? So if I give you compounds, you should be able to predict, looking at them, if they're going to be aromatic, anti-aromatic, or non-aromatic. So right, let's take some low-hanging fruit here. We got 3 minutes. We got tons of time. My first compound here, we're just going to say it's a flat ring. Does every atom in that ring have a p orbital? Nope. So then this compound is non-aromatic. You'll notice that when a compound's non-aromatic, I don't have to put how many electrons there are, right? Because the electrons, when you count the electrons, you're like, how many electrons are in the unbroken p orbital chain that I have in my ring? Well, when you don't have p orbitals on everything, your p orbital chain is broken. So you don't have to count those electrons. Flat ring. Does everything in this have a p orbital? Yes, so everything on this is part of a double bond. So we get to have our p orbitals. So we're good there. How many electrons are there total? It should be 8 electrons, right? 2, 4, 6, 8. 8 is at 4n or 4n plus 2? 4n, so that's going to be anti-aromatic. And this last one, what I wanted to point out here is this is, again, just a benzene, right? So we know it's aromatic. But we only care about the electrons that are in the ring, right? So there are electrons on this oxygen. They're not playing a part with the aromaticity. So it doesn't matter what comes off of it, right? So any substituents or anything, you're just basically ignoring those and you're just focusing on the atoms in the ring. Now there's some like little things that we can do that we'll do a little bit later, but for 99% of it, it's just like I don't care about anything hanging off of the ring. I just care about the ring itself. So it doesn't matter that the oxygen has actually 4 electrons, right? They don't play a role. All that matters is the 6 electrons in the ring. So this is aromatic. So we are going to do a bunch more examples on Friday. We're going to introduce heteroatoms, so oxygens, nitrogens, sulfurs, borons in the ring, and all the different rules for those. And yeah, we'll get through that stuff, and that should be the end of the test. So the test right now looks like it's going to have Diaz-Otto reactions, diene reactions, is this aromatic, non-aromatic, or anti-aromatic questions, and then some nomenclature stuff.